Okay, this it's not 1:30 yet. Does anybody have any question before we get started? Well, I suggested that if you want to meet us in person, face to face, we can do that tomorrow afternoon at 3:30, just outside Starbucks Cafe on MSEE, so that it would hopefully it would make you feel good that you get to meet us rather than just meeting us on the Zoom and internet all the time. Okay, so I will be on campus tomorrow to meet you all if you want to. So any questions before we get started? It's 1:30 now, so it's time to start. I suppose I can go back to my slide. And I like to wrap up the transmission line lectures on the voltage standing wave ratio. This is something quite important if you're a microwave engineer. So this word, if you're a microwave engineer, is going to be pronounced VSWR. Okay, it's VSWR. So it's like Hebrew. You don't have a vowel, but you can still pronounce this word, VSWR. Okay, what is this? Well, what happens is that when you have a transmission line, yeah, do I hear any questions?
I can't see the screen if you're sharing the screen.
Oh, let me see. Sorry about that. Thank you for letting me know. Let me see.
There we go.
Okay, can you see my screen now?
Yes.
Okay, sorry about that. As I said before, I'm going to talk about VSWR, which is the acronym for voltage standing wave ratio. So if you have a transmission line, and if you terminate it with the load, ZL, and then if you look at the voltage on this transmission line, it's going to look something like V of Z is going to be V naught e to the minus j beta z, representing a wave traveling to the right. And then you're going to have V naught e to the plus j beta z. And the reflected wave is always related to the incident wave by the reflection coefficient gamma L. Okay, so we can actually write this as V0 e to the minus j beta z. Factoring it out, I will get 1 plus e to the 2 beta z gamma L. Okay, and if you look at this function now, this we can call the general reflection coefficient, which is gamma z. Hence, I can say that this is something of this form, 1 plus gamma z. Okay, and if you look at the magnitude, in order to go back and forth between time domain and frequency domain, you will have to go through this exercise, assuming that you have a phasor. Then you would do something like this, and then you take the phasor and plug it in there, and then take the real part. Okay, so if you look at this more carefully, the magnitude of V of Z, let me see if we can show it on the left here as well. It doesn't want to stay there. I want to show part of this, okay? So if you take the magnitude of VZ now, because when you go between phasor space and real time domain space, you always have to take the magnitude of the signal. And if you were to take the magnitude of the signal, the magnitude of this is V naught. The magnitude of this part is V naught. Okay, so the magnitude will give you something like V naught 1 plus gamma Z magnitude, whole thing magnitude. So you find that gamma Z, which is not a constant, is gamma L e to the 2j beta Z. Okay, 2j beta Z. It's not going to be a constant. And you will find that on the complex plane, it can be represented by, if you were have a imaginary axis in the complex plane, a real axis in the complex plane, this number here can be represented by a number 1 plus gamma Z, and gamma Z can be pointing like this. Okay, gamma Z can be pointing like this, and this magnitude here will be 1 plus gamma Z. Okay, and gamma Z is given by this. When Z equal to 0, then gamma Z is gamma L. Gamma Z is gamma L when Z equal to 0. So gamma Z actually changes. It changes, well, if you were to go in the negative Z direction, which is actually towards the generator, you will go in this direction, you map out a circle. Okay, so this thing 1 plus gamma Z is going to be the length of the origin to the arc of the circle, depending on where your gamma L is and where your gamma Z is. You can see that this amplitude then is actually a changing function of space. And if you were to look at it more carefully, you can look at this diagram. Okay, essentially I've redrawn this diagram, that gamma Z will be pointing like this on the complex plane, and gamma L is the load, and that is the value of gamma Z at Z equal to 0. If you were to be moving towards the generator, okay, this is moving towards the source. On the Smith chart, it says towards the generator. You rotate in this direction, and if you were to move towards the load end, you move in that direction. You can see that 1 plus gamma Z will be changing its amplitude as you change your Z. And so you can say that as Z becomes negative, the voltage actually is not a constant. It will have this standing wave pattern, okay? The location of this D min and D1 very much depends on location of D min. D min means that this thing has rotated one to the other end of the circle, and if you reach this end, 1 plus gamma Z is the smallest. However, if you reach over here, 1 plus gamma Z will be the largest. Can you see that 1 plus gamma Z is becoming smaller, larger, smaller, and larger as gamma Z rotates on this circle? So the voltage standing wave pattern will look something like this. And you can actually figure out the relationship of the first maximum to the minimum, and then D1, they're all related in this manner, which means that by measuring this voltage standing wave pattern, you can actually decide what gamma L should be pointing in the complex plane originally. Okay, where gamma L was pointing originally in the complex plane. So by measuring this voltage standing wave pattern, you can figure out what the phase of gamma L should be. And then by measuring this ratio, okay, if you look at this number again, okay, this thing will be maximum this thing here will be maximum when this is maximum and when it's over here. And when it's over here, it will be 1 plus gamma z. And then when it's over here, it will be 1 minus gamma z. So you can figure out the maximum value and the minimum value very easily. Okay, you can figure out this maximum and minimum value very easily. And you can say that Vmax is 1 plus gamma z. Okay, when this is positive, and this is the same as 1 plus gamma L, because gamma z, as you know, is gamma L e to the 2j beta z. Okay, and then V min, there should be a V naught here. Okay, it's proportional to this. There should be a V naught here. And then V min would be the same thing, V naught, but when gamma z assumes a negative sign, this should be gamma L, okay, V naught. So you can actually figure out where, by looking at how it goes around in a circle, you can figure out when it will assume a maximum, that's when gamma L is pointing in this direction. Okay, gamma z is pointing in that direction. When gamma z is pointing in the other direction, you can figure out the maximum values are going to be these two values. And then the voltage standing wave ratio is Vmax over V min. Okay, it is going to be 1 plus gamma L over 1 minus gamma L. So you can measure the voltage standing wave ratio by measuring this voltage pattern. You can figure out where Vmax is and V min is. From that ratio, you can figure out the VSWR, the voltage standing wave ratio. Okay, and from the voltage standing wave ratio, you can figure out gamma L. Okay, so VSWR gives you gamma L. Okay, D1 gives you the phase of gamma L. And you can see that when you look at gamma L, it has a phase, gamma Z has a phase. And by figuring out where it goes to a minimum, you can figure out what the original phase of gamma L should be. How much negative Z you have to add to gamma L to make it become a pure real number and so on. Okay, so you can figure out what D1 is by actually measuring its location and figuring out the phase of gamma L. And from that, you can get gamma L, the complex number, will be the magnitude. Let me turn on this. Oh, what happened? Still recording, I hope. Somehow it went and closed my window accidentally. I don't know why it did that. Let me go and open it up again. Okay, I have to go and open. I would have to go and open up the PPT slide. Just have to figure out where it went. Okay, it's still here. Thank goodness. Better put autosave on. And let me go back to screen sharing again. Can you see my screen now? Hello?
Yes, it's back here.
Okay, thank you. It went away just now for some glitch that I don't understand. Let me shrink this. Okay, thank you. And then so you can actually measure the voltage standing wave pattern and measuring the location of this maximum and this minimum to figure out what the phases of gamma L should be. And then from the phases of gamma L, okay, you can actually figure out the whole complex coefficient. And here, from here, you can find ZL, okay? ZL and gamma L are related to each other because we know that ZL is Z naught 1 minus gamma L or 1 plus gamma L. Okay. So you have this kind of relationship. And then there are actually equipments to do this kind of measurement. This is just one equipment to show you. And this is another one. Okay. So are there any questions on transmission lines before I move on to the next lecture? Okay, I will not go through the detail of this. You can read about them in the lecture notes. Okay, so today I'd like to talk about multi-junction transmission lines. Transmission lines are actually very useful. They're very simple. The theory is very simple, but you can approximate a lot of things with transmission line theory, like even if you have a waveguide or twisted pair wire or even power lines, or whatever you see in microwave integrated circuits, even optical fibers and so on. You can approximate the physics of that with transmission line. This is especially so in the microwave integrated circuit. It looks very complicated like this, and there are all sorts of things on here. There might be even transistors, diodes, and different kinds of nonlinear devices. But you see that transmission lines are very, very instrumental part of this circuit. They are used to connect things together. So we like to study how to connect two transmission lines together in this lecture. The first thing that we should do is to figure out how to connect two transmission lines and figure out what the input impedance should be. Okay, say if I have two transmission lines of two different characteristic impedances with two different velocities of the wave as well. If I connect them in this manner, and if I look in this direction, what kind of impedance do I see? The first thing I should do is actually to replace this picture I have up here with an equivalent circuit down there. Okay, with an equivalent circuit down there. Let me check to see I'm recording. Okay, I want to make sure that I'm recording. I suppose I'm recording. I can't see it.
Yeah, as Professor Chu, it says it's recording.
Yeah, it's
okay.
recording.
Okay, good. Thank you. Because I can't see it from my end. Anyhow, so the key thing is to replace this circuit up there with this equivalent circuit down here. And once we know what Z into is, looking this way, we would be able to figure out what Z in 1 is, because we would be able to figure out the reflection coefficient at this end. And let's see how we go about solving this problem, okay? So the key thing is that, let me see. Z in 1 in the previous picture is Z01, 1 plus gamma L over 1 minus gamma, okay? We know this formula, and we should know it by heart, and gamma is Zn minus 1 over Zn plus 1, which is essentially equal to Z load minus Z naught over Z load plus Z naught. and Zn is the normalized value of the load, okay, normalized by the characteristic impedance, okay? And we know that gamma, the general reflection coefficient is gamma L, the reflection coefficient of the load n, e to the j beta z, okay? But in transmission lines, we always measure the origin and then we always go to the left, okay? We always go to the left and then we'll say that the location where we are doing the measurement is at minus L1, okay? Z equals minus L1, then we call this that this should be gamma L e to the minus 2j beta z, where beta z has been replaced by L1, say, okay? So we always use the formula in this manner, okay? And then Zn2, if you were to look at Zn2 in the previous slide, what should it be? So let me see. So once you know the reflection coefficient, you would be able to know what the load is. There's a relationship between the load and the impedance, and then you can figure out what the impedance here should be. But let's look at the more complicated case. More complicated case being that we have the thing connected in this way, okay? We have a load, and then it's connected to the first transmission line in this manner. And then this junction is connected to a new transmission line with a different characteristic impedance. How would we find Z in 1? Okay, the first thing we should do is to find Z in 2. Okay, Z in 2 should be equal to, let me see, Z in 2 should be equal to Z02 times, let me go up here and use this picture over here. Z02 times 1 plus gamma, okay, over 1 minus gamma, where that gamma would be the reflection coefficient, the general reflection coefficient at this end over here, okay? So if you were to look at the gamma, that gamma should be equal to gamma is equal to gamma 1 to e to the minus 2j beta 2 L2, okay? That should be the gamma that we should plug in here to find Z in 2. Okay, we should plug in that gamma and then find Z in 2 according to this formula, where this should be gamma L. Okay, let me write it properly. This should be gamma L. Okay, and then if you were to plug it in and work this out, you will find that this becomes a rather complicated formula. Z in 2 would be equal to well, let me write it out in full here first, and this can be rewritten as, let me wrap this here, this, and this will be 1 plus gamma L e to the minus 2j beta 2 L2 over 1 minus gamma L e to the minus 2j beta 2 L2, okay? Then I have to plug in the value of gamma L. Gamma L for this problem, okay, before I do this, I will have to figure out that gamma L should be equal to ZL minus Z02 over ZL plus Z02. Okay, that is the value of my gamma L. So now we plug it in, And then I would figure out that gamma 1, 2, gamma 1, 2 tilde, okay, which is the reflection coefficient at this end over here, okay? If I figure out what this gamma 1, 2 tilde should be, okay, it should be given by the value of z in 1 minus z naught over z in 1 plus z naught 1, okay? Because I'm actually replace this circuit here with one that is very much like the first case where I replaced this impedance here with just z in 2. And if I do that, then the reflection coefficient at this end over here should be just equal to that, z in 1 minus z naught 1. Let me see. Z in 2 minus, should be, sorry, this should be z in 2. Okay, z in 2 minus, so this is very much like the case of when I have a transmission line, the characteristic impedance is z naught 1, and I have a load. Okay, this load here is z in 2. And then I ask myself, what is gamma 1, 2 tilde? That gamma 1, 2 tilde would be given by this formula over here. But I have a formula, a rather complicated looking formula for z in 2 now. So I should be able to plug that in. I should plug this formula in and figure out what my gamma 1, 2 tilde should be at this end over here, okay? What gamma 1, 2 tilde should be. And then if I know gamma 1, 2 tilde, then I should be able to figure out the impedance at this end, okay? Because gamma 1, 2 tilde and z in 2 are related to each other, and so on. And then you can plug in the value for z in 2, very complicated formula, plug this back in here. And if you do enough manipulation, okay, do enough manipulation, you can find that gamma 1, 2 tilde can be written in this manner. Okay, I will not do it, but it takes quite a bit of tedious algebra. Okay, quite a bit of tedious algebra. You plug this in here, manipulate things, and then show that gamma 1, 2 tilde can be written in terms of gamma 1, 2. Okay, gamma 1, 2 plus gamma, where gamma is this complicated things over here, okay? And then gamma 1L, which is the reflection coefficient at this end, okay? Gamma 1, 2, sorry, this is gamma 1, 2. Let me write. Gamma 1, 2 is just the reflection coefficient at this end over here, okay? Gamma 1, 2 is called the local reflection coefficient. And it is the reflection coefficient at this junction, as if this transmission line L2 is infinitely long, okay? And this is gamma 1, 2 that you can show, and it is not a trivial derivation, but a rather long one. And after that, you plug in the expression for gamma, okay? Plug in the expression for gamma. The expression for gamma will look something like this, okay? Will look something like this, and I show that gamma before. Okay, gamma is given here. Okay, that expression for gamma will look something like that. And then you plug that in. Okay, you can show that finally, you can manipulate the formula to look something like this. It's a tedious derivation, which I do not like to go through, but I just want you to take the results for it. That if you have the load, okay, you can calculate gamma L at this end, okay, and then with this load, you can calculate Z generalized impedance, which is 1 plus gamma z over 1 minus gamma z naught, okay? So if you know gamma L at this end, then you can find gamma z, which is given by this formula over here, 2j beta z, okay? With this formula, you can find the impedance z at any point on this transmission line by using this formula, okay? And using this formula, then you can actually figure out what z in 2 should be. You can figure out what z in 2 should be, okay? Using this formula. And after you figure out what z in 2 should be, then you can figure out the reflection coefficient at this end, okay? Because you just use this to find z in 2, and then you can find gamma 1, 2 tilde, which is equal to z in 2 minus z naught 1, or z in 2 plus z naught 1. You have to use z naught 1 because you are pretending that you are replacing the whole thing here with a equivalent circuit, just like we did for the first case here. Okay, we take this section, replace it with an impedance, and then use that to find the reflection coefficient at this junction over here. Then the reflection coefficient is given by this gamma L, and then so you can find gamma L at this end, and then once you know gamma L, you can do the same process, because once you know gamma L, you can move this backward, okay, and find how the reflection coefficient changes as a function of z, and then you can find the input impedance at this point, okay? So finally, what you have then is that you have this very, very important formula for gamma 1, 2 tilde. This formula says that once you know the gamma 1, 2 local, okay, gamma 1, 2 local at this junction, and then if you know gamma L2 at the load here, okay, gamma L2 at the load, and if you know beta 2, you can actually use this formula to find out what the reflection coefficient should be at this end, okay, at this end. And then with that reflection coefficient, you can calculate the impedance you should see there, okay? So with this, you can extend this to 2-junction transmission line. So the process goes like, well, if you have this load here, I should be able to find gamma 2, 3 tilde at this end, okay? And if I apply the same formula, I would find that gamma 2, 3 tilde would be equal to gamma 2, 3 plus gamma L3. Let's call this gamma L3, okay? E to the minus 2j beta 2 LZ L3, okay? 1 plus gamma 2, 3 gamma L3 e to the minus 2j beta 3. This should be beta 3, sorry. This should be beta 3 L3. Essentially, I'm applying the same formula that I have derived previously. The same formula that I have derived previously to this special section, okay? To this special section, and I will be able to figure out what gamma 2, 3 should be. And if I know what gamma 2, 3 should be, I can apply the same formula again to find out what gamma 1, 2 should be. Gamma 1, 2 would be the reflection coefficient at that junction. So again, you will assume that you have a load there, a reflection coefficient there. And if you apply the same thing over again, what you find is that gamma 1, 2 tilde would be equal to gamma 1, 2. The local reflection coefficient, gamma 1, 2 is a local reflection coefficient, plus gamma 2, 3 tilde, which is a generalized reflection coefficient, minus 2j beta 2 L2. 1 plus gamma 1, 2, gamma 2, 3 tilde, e to the minus 2j beta 2 L2. Okay, essentially, I am applying this formula over again. This formula is very powerful that I have derived over here, which I did not derive. I say that it takes a lot of algebra to get there. What this formula says is that if you know the reflection coefficient at this end, okay, if you know the beta of the transmission line, you can apply this formula. And if you know the local reflection coefficient at this end, which is gamma 1, 2, okay, there's a local reflection coefficient, which is gamma 1, 2. And that gamma 1, 2 assumes that the load is infinitely far away. You can apply this formula to get the generalized reflection coefficient at this junction. This generalized reflection coefficient will consist of the local reflection coefficient plus any subsequent back and forth bouncing of the wave at this junction. Because if you see that gamma L2 is equal to 0, then gamma 1, 2 tilde is equal to gamma 1, 2, which means that if gamma L2 is 0, which means that this is a meshed load, then there will be no wave bouncing back, and gamma 1, 2 tilde would be equal to gamma 1, 2. So I'm going to apply this formula over and over again. It's a very important formula. And if I have a two-junction transmission line, I just apply it 2 times. Given the load here, I can find the reflection coefficient here. Okay, with the reflection coefficient here, I can find the reflection coefficient here. I can apply this formula recursively all the way to find the reflection coefficient at gamma 1, 2, and even at this very other n over here. Okay, so this formula allows us to solve the multi-junction transmission line problem recursively. Okay, this is called a recursive formula. So are there any questions so far? It's rather complicated derivation, but this formula is extremely important. It says that yes, yes.
So this formula is essentially recursive. Is there any explicit expression to get from Z01, say ZON, for nth link of this?
This Z01 are the property of an infinitely long transmission line. These are called the characteristic impedance of the transmission line. It is a parameter that we analyzed when we first started out on transmission line theory. We assumed the transmission line to be infinitely long, and it has lumped element and lumped capacitance and inductance, and there is a characteristic impedance that relates the ratio of the current to the voltage. Those are the Z01, Z02, Z03, and if you remember that Z is square root of L over C. So it depends on the line capacitance as well as the line inductance of the line. Each line will have a different line capacitance and line inductance. Hence, their Z's can be different. And also, each of them would have a different beta. This will be beta 1 would be omega square root of L1 C1. This would be beta 2 would be omega L2 C2. And then this would be beta 3 would be omega L3 C3. So each of this transmission line would have a different phase velocity. They might be made of different materials. Okay, but we can concatenate them using this approach to find the input impedance over here quite easily. Because once you know the reflection coefficient, the generalized reflection coefficient, you can find the input impedance. Because we have learned that once the reflection coefficient is known, there is associated with it a input impedance, a load, okay? Because on a transmission line, for every load, there is a reflection coefficient. So once we know the reflection coefficient, there is an associated impedance associated with this reflection coefficient via this formula that we have learned, okay? Gamma is CL minus Z0 over CL plus Z0, right? So we have learned this formula that once you know the impedance of the load, you know the reflection coefficient, and also we also know vice versa. Once you know gamma, you know the normalized impedance, okay, 1 plus gamma, 1 minus gamma. You can go back and forth between these two formulas. So they go hand in hand, okay? So any other questions regarding this? I did not show the detailed derivation, but you should know how to apply these formulas. Yes, another question?
Yes, I realized, but well, my question was more about not recursive relation between those gammas, but rather explicit. Like if we have set of parameters, beta 1, beta 2, so on and so forth. Do we have explicit expression for Z in, or say gamma for nth link of this chain via all this Z1, Z2, and so on?
Yeah, they are embedded in this very complicated formula. Remember that in order to calculate gamma 2,3, you need to calculate gamma L3. Gamma L3 is the reflection coefficient at this end. Gamma 2,3 is the local reflection coefficient at this end. Okay, local one means assuming that these two lines are infinitely long, and you will have a reflection coefficient. Beta 3 is a wave number that depends on omega square root of L3 over, so beta 3 is omega L3 C3. So all the parameters that you have about the transmission line will have to be plugged into this formula in order to calculate all the components of this formula in order for you to find this gamma 2,3. So you have to know what the transmission line is. You have to know what its characteristic impedance is. You have to know what the phase velocity of beta 3 or the wave number should be before you can apply this formula. And once you know those parameters, you can find the reflection coefficient at this end. And this is a generalized reflection coefficient that accounts for, in addition to the local reflection coefficient, but the subsequent reflection coefficient from the load at the far end, okay? Does this explain your question? Does this answer your question?
Well, I'm not sure, but well, I'll ask you later, probably during the office hour.
Okay, we can go over this in detail in office hours. Okay, but the most important thing is that you have to learn how to apply this formula. Okay, you have to learn how to apply this formula over and over again until you get to this end.
Yeah,
okay,
sure.
Any other questions? Any other questions? So the important thing is that most transmission lines are not ideal. They will look something like this or like this with a junction with a bend, okay? So a junction is not simple, okay? A junction usually would be something more like, well, you say I have a transmission line, I just draw the simple junction like this, Z01, Z02. That is not enough to model a junction. Usually what you need to model a junction with is actually to put in some circuits in between to model the junction. Because when you have a junction like what I've shown you in the previous picture, okay, they are excess charges, and there might be constricted current flow on this that produce excess magnetic field, and that can give rise to excess inductance and capacitance at the junction. In order to model those excess inductance and capacitance, you put in lambda element like this to account for their behavior or their contribution. So what you have learned in this course is just to have a simple junction, but when you go out as a practicing engineer, you will have to add this element to model this junction properly. These are called the stray capacitances and the stray inductance, okay? Okay, so then I'd like to move on to duality principle if you don't have any questions on transmission lines. Duality principle is a principle that exploits the symmetry of Maxwell's equation. Okay, if you look at Maxwell's equations, they're actually very symmetrical. And then we can add in fictitious current or magnetic current to Maxwell's equations as well to make it more symmetrical. And then there's this Faraday's law. I'm writing these equations in the frequency domain. Okay, and then the third one is divergence of B equals to rho sub m r of omega. I can also put in divergence of B r of omega here as well. And then I will have divergence of D, which is a function of r and omega, is equal to raised rho sub E. This is electric charges. The other one is magnetic charges. Okay, this is magnetic charges. This is electric charges. Okay, and we find that when we swap variables in Maxwell's equation, if we swap variables, okay, if we let E be H, and then if we let H becomes minus E, and then if you let D be swapped with B, and then B, let me see. B be swapped with minus D. Okay, if you go through this swapping, if you go back to Maxwell's equation, replace this E with H, and then H with minus E, and then replace this D with B and B with minus D, and then you find that Maxwell's equations are not changed. You also have to swap the current. You also have to replace M with minus J, and then J with M. Okay, we do the swapping. M with minus J, J with minus M, and then you also do the swapping of the charges. Rho M replaced with rho E, and then rho E replaced with rho M. Okay, you can do that. You find that Maxwell's equations remain the same. Okay, Maxwell's equations remain the same. This is called the duality principle. Okay, in other words, if you have found a solution to Maxwell's equations with certain EHDB, say if you solve Maxwell's equations with certain EHDB and so on, if you do this swapping, those new swapping and new solutions should still be the same solution to Maxwell's equation, except that they are dual. Okay, so this is called the duality principle. I have to add in the fact that when material is present, then the duality principle becomes slightly different. Say if I put in material, I would have to put in this thing over here, and then the second Ampere's law becomes J omega epsilon dot E plus J. And in addition to swapping the field, I will have to swap the materials as well. Mu will have to be epsilon, and epsilon will have to be mu. Okay, then I will get the same equations back, which means that if you have found a set of solutions, if you do this swapping, the new fields should still be the solution to your Maxwell's equations. Okay. Any questions on this?
Yes, I have a question.
Yeah, sure.
What to do with the thing that we have no magnetic charges, monopoles, I mean?
We are assuming that there are magnetic charges here, but and so there are some problems where you can make fictitious magnetic charges, even though we cannot make real magnetic charges. Okay.
Yeah,
and most of the time, we don't have to worry about the sources. We worry about the field only. In this course, you only have to worry about cases where you have the field and no source. And if you have sources, then you have to worry about how to construct them. Does that answer your question?
Yeah, I was worried about that. We replace essentially dipoles, magnetic dipoles with monopoles.
No, this, as I say, I want to emphasize that there are no real magnetic charges, but you can only make fictitious one. So the fictitious magnetic charges that we can make are magnetic dipoles. Okay, so if I have a current loop antenna, it produces a magnetic field that looks like this. Okay, and it looks very much like the electric field of an electric dipole. So we can say that a current loop is like a fictitious magnetic dipole. And you can actually use this concept to make current loop and line them up so that they look like fictitious magnetic current. And this resembles a magnetic current loop going around a cylinder. These are called toroidal antenna. They actually have been used in engineering, okay? So let's not worry too much about this. It can get very complicated, but I just want you to know that once you have a solution, you can solve E and H and get the other solution. For instance, if I have this problem, reflection and transmission, the single interface case, okay? And if I solve this problem, I can use duality principle, say if I replace E with H, H with minus E, and so on in this problem. And I should have a solution that's still a solution to Maxwell's equations. There's a beauty about the duality principle, okay? And you can say that if you look at the TM polarization for this problem, a plane wave coming in, a plane wave reflected, the plane wave transmitted, okay? These two problems are dual to each other. Once we have solved this problem, we can solve the second problem quite easily. And that we can do by invoking duality principle, okay? Let me see. I like to speed up a little bit so that I can have the solution to this problem solved in front of you. I say that once you solve this problem, for the TE polarization, where the electric field is pointing out of the paper, magnetic field is pointing like this, okay, transmitted field is pointing out of the paper, electric field is pointing that way. Once you solve this problem can be found by invoking duality principle, okay? So let's go about solving this problem in some greater detail then. This is called the TE polarization, because the electric field E is transverse to the direction of propagation of the wave. It's also transverse to the Z-axis, okay? It's transverse to both axes, and we call this the TE polarization of TE case. And they're given different names in the literature, and I will elaborate those in the lecture notes. So let's look at the TE case then. Okay, TE case. Well, we assume that EZ equal to 0. That is, the field is only in the X and the Y direction. Let me see if I... Okay, the field is only in the X and the Y direction. Actually, in this case, actually the field is pointing in the Y direction, okay, pointing out of the paper. This is a TE polarization, okay? So then I can write down the incident plane wave. The incident plane wave would be equal to a Y polarized wave multiply with a certain amplitude, and then it will have a certain wave vector beta. Let's call it beta I dot R. Okay, I use this to mathematically represent this wave coming in at me. Okay, this wave coming in at me. Okay, and if I write it explicitly, then it should be, I don't know why it jumps back up again. So it doesn't want to stay down there. So it is, it jumps back up again. E naught e to the minus j beta x x, and then e to the minus j beta r and y y. No, sorry, this should be just y. So if I write out the exponent explicitly, this is what I should have. Sorry, this should be z. Okay, because my k vector is pointing in the xz plane. My beta vector is beta z. Okay, my beta vector is pointing in that direction. And then there should be a reflected wave, the reflected plane wave. I will assume that the reflected plane wave is of the same polarization. Okay, you might like to ask why. Why is it of the same polarization? Let's assume that it is first and see if you can match the boundary condition. If we cannot match the boundary condition, then we scratch our head and go back to the drawing board and assume more. Okay, don't assume that it's just Y polarized. But at this point, to simplify our life, we make the reflected wave to be polarized in the Y direction, the same way as is the incident wave. Then if I write this out explicitly, then I would have RTE here. And then I will have e to the minus j beta RXX minus j beta RZZ. Okay, I'm going to assume something. I'm going to assume that the beta I or beta R is going to have a component of the Z vector that is of opposite sign. Okay. Because in this picture, I see that the beta has a negative Z component, a positive X component as I drew the picture. So I'm going to assume that the beta is going to be something of this form. Why does it always jump up? Maybe this will not make it jump up. Okay, so because of that, I'm going to change the sign here, indicating that this thing is actually propagating in a negative Z direction. Okay, and then the transmitted wave, okay, would be a plane wave in the transmitted region. I assume again that it is polarized in the Y direction for simplicity. And then if I write it out explicitly, okay, then it will be beta TXX minus J beta TZZ. Again, assuming that beta T is X beta TX plus Z beta TZ, okay? So then I will have to match boundary conditions. There are two unknowns here. The unknowns are RTE and TTE, okay? Two unknowns. So I need two equations and two unknowns. What kind of boundary conditions should I have at the interface? Does anybody know? I think some of you might have studied this problem before.
Tangential E field should be 0.
Not 0, because it's not a metallic interface. Tangential E field should be something else.
There should be equal.
They're continuous. Okay, tangential E field in the top region and the bottom region should be equal to each other. These are the total field in the top region. This is at the bottom. Okay, so those two fields should be equal to each other. There's one thing. And so if we were to set z equal to 0, which is where the interface is, then we look at the tangential E field. Tangential E field is a y component of the electric field. Then if we equate the equations, then we will have z0 e to the minus, if I look at this expression, minus j beta ixx. I set z equal to 0, okay? Set z equal to 0. Set z equal to 0. This expression will be incident wave. But then I have to also add the reflected wave. Reflected wave will be this thing. And then it will be e to the minus j beta rxx. Again, I set z equal to 0, so this term goes away. And that should be equal to the tangential E field on the other side. On the other side, I only have one wave. So it'll be E0 TTE, okay? E to the minus j beta txx, okay? And this has been meshed at z equal to 0, but this is going to be equal to each other for all x, okay? The mathematical symbol for that is for all x. And these two equations, these two expressions cannot be equal to each other. There's no way for them to be equal to each other for all x unless you have beta ix equal to beta rx is equal to beta tx. Okay. If this is true, then I see that all the phase factors that I have are equal to each other. Okay, and then I can cancel them out. Then I have a chance of having this equation being equal to each other, left-hand side and right-hand side all the time. Okay, this condition is called phase matching. By phase matching, then I can also cancel out this because E0 is common to both sides. I end up with a simpler equation. 1 plus RTE is equal to TE, okay? But this is only one equation. I need another boundary condition to obtain another equation in order to have two equations and two unknowns and solve for them. What do you think the other boundary condition should be at this interface? Anybody?
The normal component of the magnetic field should be continuous as well.
You're correct, but that is not the right one. Maybe we should go back. Okay, we went through boundary conditions. We went through Faraday's law, and then we have Ampere's law, and then we have Gauss' law, and then we have Gauss' law for magnetic field. Each of them induces a boundary condition. What does Faraday's law induce in terms of boundary condition? Does anybody remember? If you go back to your lecture on boundary condition, Faraday's law induces a boundary condition. Does anybody know what that is?
It's a tangential electrical field equals to each other.
Very good. Okay. N cross E continuous. Okay, that's what Faraday's law induces. What about Ampere's law?
Same here, the tangential components of magnetic field are equal.
Right, for source free. I have to assume that source free, no current sources. Okay, if your current sheet, that's not true. And then this one is what? N dot B continuous. Okay, this one will give you N dot B continuous. Okay. So somebody say something, and we already use this first boundary condition to solve this problem. So we need the second boundary condition in order to come up with the second set of equations. Okay, somebody mentioned something about normal B or normal B. Okay, But if you have a choice in choosing these 4 boundary conditions, which 2 would you choose and why? Okay, I would have chosen the first 2 because the first 2 boundary conditions have actually more substance in it. It says tangential E is continuous. There are 2 components of tangential E field. Tangential H is continuous. There are 2 components of tangential H. Normal D is continuous, only have 1 component there. Okay, so these 2 boundary conditions are not as rich as these first 2. There's one other thing. The second thing is that we know that the third and the fourth Maxwell's equation are derivable from the first 2. This also implies that whatever boundary conditions that come from the first 2 equations are also embedded in the boundary conditions that come from the third and the fourth. Do you get it? Since third and fourth is derivable from the first 2, we emphasize this many times in this course, which means that the boundary conditions that you have derived from the first 2 are more encompassing than those that come from the third and the fourth. Okay, so we would look for the second boundary condition in order to solve this problem. What would be the second boundary condition that you should use? Anybody?
Replacing the magnetic field with negative electrical field for the tangential.
No, that was applying duality principle. You're jumping too far ahead. I'm going to remain within this problem, okay, of the single interface reflection problem, okay, and then ask myself, I have 2 unknowns to solve for here. The 2 unknowns are RTE. The 2 unknowns are RTE and TTE. What does this show up? Okay, I don't want you to show up. Okay, so I need one more equation. One more equation to solve for the 2 unknowns. Okay, so what should I do? What is the other boundary condition that I should invoke?
We can write the continuous equation for tangential magnetic field.
Yes,
There is no currents on those.
Right, there's no current source in this problem, so I should look for the use of this boundary condition. Tangential H is continuous. So in order to impose this, I have to find the H field associated with the E field. I have written down the E field in this full glory. Okay, I have written down the E field in their full glory, and then I just have to derive their corresponding H field. Well, in order to do that, I have to go to Maxwell's equations. I say that curl of E, given the E field, I can always find the magnetic field using Faraday's law. Okay. And since these are all plane waves, I'm dealing with plane wave, then my del can be replaced with J beta. Okay. And hence Faraday's law just becomes J beta cross E is equal to J omega mu H. Oh, sorry, there should be a minus sign here. Minus J omega mu H. Okay. So you can actually figure out the incident field by applying this equation. Again, lots of algebra. I don't think you can do electromagnetics without having to go through the pain of doing the algebra. Okay, and then you can figure out HR. HR would be beta R cross ER dot omega mu 1. And then you can also figure out HT, which will be given by beta T cross ET over omega mu 2. I have to use mu 2 now because I'm in the second region. Okay, and then you can go through the exercise. Then what you find is that the magnetic field, if you take the electric field and apply this operation to the magnetic field, you'll find that the magnetic field equivalent to the electric field for the first term, okay, for the first term will be something like this, okay, and it will be beta IZ over omega mu1 E naught e to the minus j beta ixx, and that is the magnetic field equivalent to that term. And then you also can apply this operation, okay, to find the reflected field to this second term here, okay? And you'll find that it would be something like this, beta tz, sorry, not beta tz, beta rz over omega mu2, and then E naught RTE e to the minus j beta rxx. And then you would do the same thing to the right-hand side, find the corresponding magnetic field that corresponds to that. In other words, you go in here, find the magnetic field and plug it on the right-hand side, and then you will find that, oops, you'll find that this becomes beta tz over omega mu. Sorry, this should be mu1. Should be mu. This should be mu2 now because I'm in the second region. Okay, TTE times E naught e to the minus j beta t xx. Okay, again, I'm assuming phase matching. If I assume phase matching, all these phases are equal to each other. They can cancel, E naught can be canceled. Okay, and then I'm ending up with an equation that says omega can cancel each other on both sides. And then I'm ending up with the equation that says that beta Iz, okay, beta Iz over mu1, and then 1 minus RTE. Okay, you can show that beta RZ is equal to beta Iz. Okay, that you can show. And then I can call both of them equal to beta 1z. Okay, so the left-hand side would be equal to that. And then the right-hand side would be beta tz over mu2 TTE. Okay, I would have that on the left-hand side. Okay, why is beta Iz and beta RZ the same as each other? Okay, the reason is very simple because these are plane waves. And since they're plane waves, they have to satisfy the dispersion relationship in their respective regions. Okay, what it means is that, let me insert it. What I mean is that in region 1, beta Rx plus beta Rz square must be beta 1 square. Because it is a plane wave in region 1. For the incident wave, that is also the same. Beta Ix square plus beta Iz square must be equal to beta 1 square. Okay? And we are already saying that by phase matching, beta Rx equal to beta Ix by phase matching. Phase matching. Okay, if you look at this equation, okay, beta 1 square is the same. And then this implies that beta Rz is equal to beta Iz. This is I. Okay, so you can just eyeball two equations and they must be the same as each other. So because of that, I can assume that beta Iz and beta Rz are equal to each other and they are equal to beta 1z. Okay, and then beta Tz, I can call it beta 2z, the wave number in the second region. Okay, so now I have two equations and two unknowns. Okay, the two equations and two unknowns. One of the equations is this. The other equation is what I had previously. Okay, I had previously, which is given by this slide over here. Or is it not showing up? Ah, this one over here. Okay, and two equations, two unknowns, and it's a simple algebra to show that, well, I won't go through the algebra with you. I'm sure that you can do it yourself. You can do it at home, okay? So if you do that, then you will find that these are the reflection coefficients. Okay, and so if you compare with transmission line formula, gamma is Z n minus 1 over Zn plus 1. So it is something like ZL minus Z naught over ZL plus Z naught. So there's some similarities, as you can see there. And then TTE is 1 plus RTE. Then you can figure that out, okay? It's written down in the lecture notes. I won't write it down, okay? And then you can apply duality principle. You can apply duality principle in the sense that once you have solved the first problem, okay, you can solve the second problem by swapping the field, E with H, H with T, but second problem is for TM polarization. The first problem is for TE polarization. So you can obtain the solution for TM polarization right away. Okay, you can apply that duality principle and get the solution for RTM. RTM would be just beta 1 Z1 epsilon 1. So you have to swap material. Remember, epsilon and mu have to be swapped when you have material properties. Okay, and then, so you just swap them, okay? I'm not going to write them out in full. Okay, and then you can find your TTM2. Okay, these are called the Fresnel reflection and transmission coefficient. Okay, are there any questions before I call it quit for today? Any questions? Anybody? Yes.
No. Okay, I have a question on boundary conditions.
Oh yeah, go ahead.
So we have basically duality principle for Maxwell's equations, and we obtain those boundary conditions from Maxwell's equations.
Mm-hmm.
Are those does it mean that those boundary conditions are also dual to each other, or there are some problems with them?
The boundary conditions, what do you mean by dual? They are tangential E continuous, tangential H continuous. There's always a truth. There's almost like a universal truth. Okay, so there's no dual to each other, because those equations are derived. Assuming that Maxwell's equations are source-free, okay, if you assume that Maxwell's equations are source-free, okay, you can swap E and H, but you get the same conclusion, tangential E continuous, tangential H continuous. These two boundary conditions are always universal. You can say that they follow from duality, but it's like hitting a thumbtack with a sledgehammer, because you can see that this equation implies tangential E continuous. That equation implies tangential H continuous. Are they related by duality? Yes. Yeah, they're related. I swap E and H, I get the same boundary condition, but I wouldn't go through that pain to say that.
Yes,
Okay.
I mean, there's a minus sign in Faraday's law, and doesn't it affect somehow those conditions?
Yes, remember, the boundary condition came from the derivative operator, not whatever happened on the right-hand side, unless the right-hand side is a current source that is highly singular. And if I assume that this problem to be free of current sources, then the only thing that controls the boundary condition are these derivative operators. There's no sign change in this equation. It says that E has to be a finite quantity so that when you take its curl, it gives you a finite quantity, or E has to be continuous in such a fashion so that when you take its curl, it does not give you singularities. Similarly, if there's no singularity on the right-hand side, H has to be continuous in such a manner so that when you take its derivative, you don't get any singularity. The same thing for this equation 2, divergence and divergence of D and divergence of B. Okay, does this answer your question?
That's clear.
Okay, good. So any other questions? Well, I make an opportunity for you guys to meet us tomorrow at 3:30 on MSEE, so that you know, I kind of depressing that you never see your instructor and never see your TAs and never see your assistant instructor. So tomorrow afternoon, I give you a chance to meet us and we can have some chat together and about how we can improve the course. Okay? Is that fair? If not, then I'll let you go then.
Yeah, sounds cool. Thanks, Professor.
Okay.
Yeah, thank you.
Thank you. I see you tomorrow if you do come tomorrow. Okay.
Okay.
Thank you, Professor.
Okay. See you. See you later.
Thank you, Professor.
Okay. Thank you.
Professor.
Thank you for coming.